Okay, welcome everybody. This is now our fourth Langtangen seminar. We're happy to have you all back with us. Today, I'm happy to say that we have Carola Schönlieb from the University of Cambridge who will be our speaker. Just a few words about Professor Schönlieb. So she works in image processing, as many of you probably know, but also in partial differential equations, or let's say this analytic perspective of image processing. Professor Schönlieb is a fellow of Jesus College at Cambridge, and also at the Applied Mathematics Department in Cambridge. She received her PhD in 2009, also from Cambridge, and then had a brief stint in Göttingen, I believe, and then returned back to Cambridge in 2010 as a lecturer. She has many accolades, among them the Whitehead Prize of the London Mathematical Society, a Leverhulme Prize in 2017. She is a fellow of the Alan Turing Institute and director of the Cantab Capital Institute for Mathematics of Information, and many other things as well. And I'm also happy to say that she was a SIAM Fellow for the class of 2024. So without further ado, Carola, the floor is yours.
Okay, thank you very much, Thomas, and thanks a lot to both of you, Thomas and Marie, for inviting me to give this talk. Um, so what I have been planning to do is really to share my passion for mathematical imaging with you by taking you a little bit on a both historic journey as well as methodological explanation, mathematical explanation of what the recent developments are within mathematical imaging, in particular in the context of structure preserving deep learning for imaging. And within that, what I'm mainly focused on is inverse problems in imaging. So where what you're measuring is not an image directly, but the whole mathematical challenge is to extract something indirectly hidden in measurements, like what you get in most of medical imaging. And I'll make that more precise in a moment. So I always start by really thanking my research group in Cambridge. I have a very large group of PhD students and postdocs, which are mainly explained by the remit that we have, which is really taking mathematical developments to applications, to quite a diverse range of applications, and without them, nothing that I'm going to tell you would have been possible. So thanks so much to these wonderful people. And yeah, so this just makes it more concrete what I said about the size of the group. So these are the topics that we are covering. So when I say mathematical methodology, mathematical theory, what I mean is, and Thomas has hinted towards this already, is more analysis viewpoint onto image processing. So my background originally is in nonlinear PDEs. I actually started out not looking at imaging at all. I looked at the Cahn-Hilliard equation and some stationary states there. And that same equation actually brought me into imaging, which is another story, not for today. So it's partial differential equations, variational models, which are of course very much linked to PDEs, and which have played a really crucial role in setting up the analysis viewpoint onto image processing, I would say in the 90s, and since then still a very, very important framework for formulating methodologies within image processing. And then, of course, optimization very much linked to the need to computationally solve PDEs and variational models. And I would say for the last almost 10 years now, a lot of machine learning. And so here on the left, what you see are the kind of image processing tasks that we are solving, that we are targeting. And on the right, you see all the applications that pop up in the interdisciplinary research that we do, which is very much the source for all of these problems you see here on the left. And I'll make that more concrete and with more pictures in a moment. So very much again with maybe some kind of numerical analysis, PDE head on. I'm going also to approach to explain to you what mathematical imaging is, which is first starting macroscopically. Okay. So I'm just starting with a one-liner of what I think mathematical imaging is. It's the study and development of mathematical methods that are much more than what I just had on my first slide, right? The analysis viewpoint is just one of many mathematical perspectives onto imaging. And what is imaging? These are problems in image analysis, image processing, and inverse problems in imaging, which, as I said, will be the focus for the one case study, for the one more deeper investigation that I will discuss. So I'd like to give you a first impression onto mathematical imaging with an outreach video that we did a couple of years ago together with Samuli Siltanen, who is this person here on the left from the University of Helsinki, who since then has actually, I think, outreach has become one of his main activities. So he's a really wonderful communicator. But for that, I need to break the screen share for a moment.
Samu, you want to remove things from photographs, right? That's right. Can we try? Sure. Can you make the code disappear? Okay. Watch it. All right. I think I can still see something. Yeah, that was harmonic in painting. Okay. We can try total variation in painting. All right. Okay. Pretty cool. Isn't it? All right. Can we try some more stuff? Yeah, that would be fun. All right. Let's do it. Try. That's pretty cool. Yeah, that's the power of applied mathematics. But can in-painting make us disappear? Sure.
Okay. So I hope you saw that, but no one complained anymore, so I'm guessing that worked. So let's go back to the presentation. That was really just to give you a taste of the kind of things that mathematical imaging people worry about. So you've seen in the different methodologies, the different, harmonic and total variation in painting and patch-based in painting and so on. The main there were quite a few differences of how the in-painting result looked like, right? And getting that right, getting that visually pleasing is one aspect of imaging, right? Is trying to derive mathematical equations that can model how images look like, basically. This is the art of it. Okay. So without further ado, let's go into the actual plan of the talk. That was really just a taste of it. I want to now give you a little bit more about the kind of problems we want to solve and how we can mathematically formalize them. why we actually want to solve them. So they're really, you've seen in the many interdisciplinary collaborations that I've listed, there is really lots of exciting problems awaiting a mathematician to look at. And there is also a variety of different mathematical lenses that people have taken onto mathematical imaging problems. And again, while I'm only going to cover a very tiny proportion, I just want to give you an overview of what the different areas are that appear, and then dive into one example, which is about computer tomography imaging and how to make that better under very low resource settings. Okay, so what are the problems we want to solve? Again, starting macroscopically, really the common goal often is to extract information and really robust information and in an automated way from large and diverse and most of the time, well, I would say actually all the time, corrupted imaging data, imperfect imaging data due to mostly properties of the measurement process. And here are just a few examples that are really just for visually pleasing you while I'm talking about mathematical imaging. Here I want to go through these examples in a more systematic way. And here I'm really at the moment talking at the level of tasks, right? So what are the abstract mathematical tasks that people want to solve in imaging? So one really overarching thing that appears all the time, right, in all the different applications, even when you want to do things here that I have here on the right, something that you always need to worry about is noise in the noise in the image. And so this goes, if you just consider the task of removing noise from images, is called image denoising, and you can formulate it here in saying what you measure. And this is usually the letter that I'm using, so the variable that I'm using for the noisy image is going to be y, or for the noisy data is going to be y. This is a noisy version of the image u, the clean image u that I, of course, don't know, right? That I want to estimate. And the estimate I call here u star. And I've modeled here the noise as an additive component, but that is not, there could be many other scenarios. And again, there are lots of other informations that go into even just, before you start formulating a mathematical solution to that, which is, what is the distribution of the noise? What are y, u, and n here? Are these vectors? Are these infinite dimensional objects? This also very much depends on the mathematical lens that you're taking, right? So as an analyst, I would start out saying y, u, and n are functions in infinite dimensional function spaces. And then I formulate based on that and specific choices for these function spaces, I formulate a mathematical solution. But people in statistics would maybe more look at y, u, and n as vectors in Rn or Zn or whatever your that depends again on the type of measurements you're taking. So that's a starting task that always appears. A slight alteration of image denoising, which makes, though, a huge impact on the mathematical problems that appear and the mathematical solutions, is if you put into this equation now also a so-called forward operator. Okay, so this is here modeled as capital T, where you say, well, actually what you measure is not a noisy image, but is a noisy version of some transform of this image. And this, as I said at the very beginning, happens a lot in medical imaging or in scientific imaging in general, I would say. that you have machines like tomography machines, for instance, that measure a transform of the image. Yeah? So in tomography, the capital T is the so-called X-ray or radon transform. Yeah? So it takes line integrals through the specimen that you want to image. And from these line integrals, you want to reconstruct an object. You want to reconstruct, here in this case, the tissue density in computer tomography. Okay. The tasks here that I have on the right are more quantification tasks. The tasks that I have on the left are more kind of processing tasks. Okay. So on the left, the main tasks are reconstructing an image that contains in a reliable way the information that my measurements have that my data has measured. But at the same time getting rid of all the kind of obstructing things like noise, or maybe even in the context of imaging painting, obstructing things like gap that you have in the measurements that you have taken. Okay. So the right is now quantification. So you have some image data. Maybe you have even already cleaned it up. You've reconstructed an image from some indirect measurements, and now you want to quantify something on the basis of this image. So here I've put two prototypical examples. One is segmentation. So you have an image. You're not interested in every single bit in this image, but you're interested in certain objects. And you want to draw boundaries around these objects and then, well, do something else with the object. But mathematically, you can formulate it like this, that you've given an image on some domain, usually a rectangular domain. This is one way to formalize segmentation, is to say, I'm looking for subdomains in terms of the characteristic functions of these subdomains in the image domain. Okay. And I think I have an example, a variational model that picks that up and formulates this then to say, I'm looking for characteristic functions of these domains where I'm imposing some regularity assumptions on the boundary of the domain, and at the same time say something about what happens inside and outside of the domain. So this is one way to think about how to, from first principles, come up with a reasonable segmentation algorithm to say, inside the domain, I have a certain gray value. Outside of the domain, I have a certain gray value or color value. And then I have some conditions on the boundary. Maybe I have a sharp gradient at the boundary, and I maybe want also some smoothness assumptions on the boundary. Okay, I'm already telling you too much, actually. I'm going to move on. Okay, classification is another example that is in a way related to segmentation, but it's a bit more general. So here I want to, on an image level, I want to decompose an image not into just inside and outside one domain, but I have multiple domains. I want to decompose the whole image into different types of objects. And here in this example, this is a satellite image, and I want to decompose the image into different types of land cover, for instance. Okay. Or the other type of classification is I have a data set of images. So this is what is written here. And I want to assign to each image a different label, right? So like cats or dogs or something like this. Okay, so why do we want to do all of this? I have not really told you too much about all these applications here, which I'm now going to do. And by the way, all of this is very anecdotal, right? Because I'm taking a lot of examples, of course, from the kind of things that we have been doing in the group. There are many more things that other people have done, of course. Yeah. That's what you're going to hear today. So the first example here, actually on the starting slide, is the first interdisciplinary collaboration that I had when I started in Cambridge, which was a collaboration with a zoologist. And it was, I would say really a very, one nice thing about interdisciplinary collaborations is also that you learn a lot about the other discipline. And in this case, if not more, what I've learned is that some researchers are very creative and very courageous in their approach. So this was a junior research fellow here, which is like a Cambridge postdoc kind of thing. And she was interested in these pied flycatcher birds. And in particular, she came with the hypothesis, this was her starting hypothesis, that the male species of these pied flycatcher birds has, so the male species has this white blaze on their forehead. And the starting hypothesis was the size of this blaze is correlated with their sexual productiveness. Okay, with their sexual reproductiveness. And so what she did was, these are migrating birds. They come to Cambridge to breed. And so they have like little nesting boxes outside of Cambridge. And so what she did is she went to these nesting boxes. And I mean, you can almost see what she did. She did this all by herself, right? So she caught the bird, she held the bird in one hand, she had some measurement device in the other hand, or in the same hand, in fact, and then she took a picture with the other hand. Okay, and then our tasks was comparably actually easy, right? Because we were left with a database of these images. And the task, again, I guess is self-explanatory. She wanted to measure the size of the blaze. And so like this was, this I've only have there for sentimental reasons, really, because I think it's a more niche example. But there are many examples where, of course, images appear and where people need some automated processing to answer the research questions that they're actually interested in, right? So here are a few examples from a wide range of different application areas, where I'm starting out here with an example from remote sensing. In particular, LiDAR. LiDAR is a form of it is another version of radar, just with light, basically. So you measure the light reflectance that is coming back to your sensors. And from this, you get a point cloud. So you can measure this from flying with airplanes over certain areas you're interested in. Here we have been working with people in forest conservation and forest ecology, who are interested in quantifying and also monitoring health of forests over time and biodiversity and so on and so forth. And so the starting tasks that we looked at with them is segmentation of individual trees out of these LiDAR point clouds. And so here you can see one result of that, of what we did there. In this case, this was many, many years ago. This was just was a simple graph clustering algorithm where we used as a way to cluster the points, we used the one Laplacian to do this. The next example is an example of image to image or imaging measurements to image. You want to get the best out of measured imaging data under the constraints, again, of the physics, of the measurement noise, and the constraints of the forward operator, in the case here of magnetic resonance imaging is the Fourier transform. And under certain assumptions, and this is the thing you can take advantage of, certain assumptions that you have about the objects that you're imaging, some smoothness, regularity assumptions that you have. And so this is an example in spatiotemporal imaging, so where you're both interested in the best resolution you can get in space, in XY or in XYZ, could also be three-dimensional, as well as in time. And what in particular is interesting in the spatiotemporal case is that imaging, usually the resolution in imaging in the spatial resolution correlates with the amount of time that you can take to take a measurement. So in magnetic resonance imaging in particular, it amounts to how many Fourier coefficients can you actually measure. And measuring them takes time. So on the other hand, if you want to look at something dynamic, you also would like to have a high time resolution, which means that you can't take as many measurements in space that you would need for space, or in MRI in the frequency domain per time step. And so here the trade-off between spatial temporal resolution and in particular the question how much can you complement the undersampling that you do in space and time by prior information that you have about the behavior of the image in space and time is one of the main mathematical questions here. Yeah, and so one prime example of a whole area being created out of this is compressed sensing, where people are trying to reduce the amount of measurements that they take and still reconstruct something that well approximates the underlying ground truth. The next example is traffic. Traffic quantification based on just videos, roadside videos. Actually, this is just a benchmarking example, but this was a collaboration together with India, where we looked at traffic camera data. And based on this, basically detecting different types of vehicles, different types of modes of transport. Yeah, this could also be pedestrians or cyclists, and quantifying how many there are. So in this case, this is already an example where the main model behind solving this is actually a deep learning model. Okay. So a machine learning model. Bottom left is an example from digital humanities. This is another very big focus area of the kind of work that we do here in Cambridge, is cultural heritage, art restoration, and also conservation. And here, one of the main topics that we have been looking at is virtual art restoration. So if you have some artifact, in this case, this is an illumination from a manuscript, from a historic manuscript, based on scientific imaging data of this manuscript, which in this case is spectral imaging as well as just a normal photograph. Can you reconstruct? Can you go back in time and show us how this illumination looked like before it was altered? And in this case, it was really altered. In this case, it was overpainted. This was a manuscript, an illuminated manuscript that showed the biblical story of creation with Adam and Eve in paradise, and at some point in time, so originally these were naked, as they, looking at the Bible as they were before the incident with the apple happened. And at some point in time, though, some later owner didn't really like that and overpainted them and put skirts on them. So what we did is just try to recreate how it could have looked like before. And the nice thing is with infrared, this is what you saw just before with infrared, with the infrared channel, you could actually look through the skirt. And so what we did, this is an inpainting example. What we did is just use the structures we could see and outline through the skirt impaint the skirt along these structures with some kind of drift diffusion equation. This is really just the PDE that we're solving on this domain with boundary conditions and with a forcing term that encodes the structures that you can see through the skirt. Yeah, so yeah, so. This is the next example is from molecular biology, is modeling protein dynamics. And so here, this is an example, actually a relatively recent example that we started with a former PhD student of mine, looking at reconstructing atomic models from tomographic measurements, basically. Yeah? So this was the main thing I have done there. And the last example is a lot of times imaging appears also as a kind of service to people in other disciplines, and that it just helps them to reduce the amount of boring work that they need to do. Yeah? So it reduces the amount of manual labeling that people need to do, like automated segmentation is a very good example, right? That appears in a lot of biology, medicine, where, if you don't come up with an automated tool that really reliably helps them and counts things or segments things, they just need to do this by hand. Or like in the picture that you see here, could a very powerful thing about imaging, and maybe, if you want artificial intelligence as a whole nowadays, is that it can draw connections between one individual you are looking at and multiple individuals, patients that you or other colleagues, if you're a clinician, have seen before. Right? So finding patterns in data sets, in populations, in data sets of populations of individuals is very, very powerful in medicine nowadays, of course. And so this is another example of a lot of the motivation and interdisciplinary collaborations that are coming through. And here, by the way, maybe interestingly, I didn't choose this on purpose. I'm just realizing this now for the first time. The same type of approach that we're using here, this is an example where we have a data set of chest x-rays and we want to classify them into different pathologies. We abstract this problem into a graph clustering problem, right? So each image here, each chest x-ray image is a node in your graph, and then you want to label it, you want to color the graph, and each color represents a different pathology. Same, actually almost the same algorithm we have used here for the trees, although here the graph, right, the points here are really physical spatial points, versus here these are just points in a feature space, if that makes sense, right? So we just we just took the chest X-ray image and we computed features of this, and this makes up a coordinate in a high dimensional feature space, each feature. Okay, so I've already said a lot on a few slides, but let me tell you a lot more now. This is the last kind of overview slide. So how do we now solve these approaches? You've already seen a little bit. I've briefly mentioned some of the things we have been doing here and there. But again, to give you a broader overview, what are the things that appear? What are the type of mathematical models that appear? So again, starting on the top left, a lot of times, and again, the ordering in which I've put things are, of course, also colored by my analysis viewpoint. But a lot of times, something that has been really a toolkit that has been extremely powerful, since Lyons, I would say, started out with total variation regularization. Lyons and Chambol and so on and so forth have really started off the field of modeling images as functions in bounded variation spaces, basically. Since then, this whole field of partial differential equations modeling images has been huge. And several people who have been my role models when I grew up have really made their career in coming up with different PDEs and variational models for image processing tasks. So here the idea is really that the image itself is a solution to this PDE or a solution to an associated variational model. And where the PDE itself characterizes the image in terms of regularity, but could also characterize it in terms of some geometric structures that you can describe well with derivatives that you see in the image, if that makes sense. So like image edges, for instance, right? So image edges is maybe, edges are boundaries between regions in the image that have different intensities, right? Significantly different, right? It's not a gradual change, but like a step change. And so first of all, this might already tell you that bounded variation functions might be a good model for them because they allow discontinuities in the solution. But what that also tells you, this is a geometric property, right? So this is like edges can be well described by, for instance, saying that the gradient of the image, the derivative of the image is large. Another viewpoint is the applied harmonic analysis viewpoint, which says, well, derivatives are a good way to characterize some features in images. Another way is to think about more general dictionaries, right? More general expansions in which I can represent my image, right? So I can say my image I can represent in some linear combination of dictionary elements psi, and now the goal is to determine what the coefficients are. And well, and another important thing is the choice of the dictionary, of course, right? But you can think of a lot of problems, both in terms of image processing and image analysis tasks have been formulated by saying, I'm looking for, given this dictionary, I'm looking for the best coefficients that can help me approximate an image and get rid of noise and things like this. And of course, an important component here is a sparsity assumption. So that you can actually find a dictionary that helps you to represent this image in an efficient way with a small number of non-zero coefficients. Another topic that, of course, appears a lot is numerical analysis and optimization, right? Once you have formulated a PDE, a variational model, you need to numerically solve it. And so this usually ends up, so I think I have 10 more minutes, this usually ends up in being some kind of nonlinear iteration that you need to go through in order to compute the desired image in the limit or segmentation or whatever you want to compute. Differential geometry pops up from time to time because in the situations where the imaging data that you're measuring or the solution or whatever you want to extract from the imaging data lives in a nonlinear space, in a curved space. And so here, for instance, in the previous example, in the protein dynamics example, this is an example where differential geometry is crucial because you're reconstructing this atomistic model, which lives on a manifold and not just in Rn. But there are many more examples, in particular more towards computer vision and people in graphics and so on, where shape spaces and discrete versions of shape spaces and so on come up. So there's a lot of differential geometry there. Statistics, of course, is an important topic because measurements, when they're taken, I mean, already starting with the fact that these measurements are noisy, they follow some distribution, and here you are, there is statistics coming up here. So modeling this and also being able to give guarantees on how well, under certain distributional assumptions on the measurements, how well you can reconstruct an image is a whole area in statistics, right? And in particular, Bayesian statistics is important here because you also might want to quantify the certainty with which you can reconstruct these images. And then the last thing is machine learning. And of course, I don't need to say much more for that. It enters a lot of areas in mathematics and beyond nowadays. But the main thing I would say, and again, thinking back to the video that I've shown at the beginning, the main reason why machine learning has really kicked off in imaging so much is, first of all, because there are lots of images digitally available. So there is a huge training database that people can use. And then modeling images mathematically is just really hard, right? And it makes a lot of sense to think that we can do a better job in modeling prior assumptions for images when using actual data to come up with a good model. So that's, I guess, the machine learning pitch in mathematical imaging. And then there are a few more here. I think mathematical imaging is one of these fields where a lot of different types of mathematicians have been looking at it, just because I think it's very pleasing to do mathematics with an immediate visual response. And so this is reflected in this. Okay, so very briefly now, let me give you an example of where we are in mathematical imaging, more generally, I would say, which, if I go back to my previous kind of slide of the different mathematical areas, takes, positions you somewhere in between coming up with models from first principles. Okay, so thinking about a problem and writing down an equation for the image, writing down an equation for the measurements, for the forward operator, thinking about the different mathematical properties that they have, and also thinking about constraints like computational constraints that you have. Being between this kind of principled way of doing things and the machine learning, in particular deep learning way of people now really making use of the deep learning tool by taking advantage of data that we have to complement some of the mathematical models that we have come up with. And so let me give you one concrete example for that, which is in the context of computed tomography. So this we've had already. I think I will go over this quickly. Let me just give you here the mathematical model that this example will use, which is variational. The variational approach is the variational regularization approach, where the solution of the computed tomography problem, so reconstructing an image from line measurements, is phrased as a minimization problem, where you're looking at a minimizer U that on the one hand fits your model for the data, okay, in some way. Think of it, for instance, in the least squares fit. For simplicity, I've just taken here a linear forward operator. Okay, so just think of this either if you're in finite dimensions as a matrix or as a linear bounded operator in infinite dimensions. So this is one condition on the minimizer, and then this is now complemented by all the kind of prior structural assumptions, regularity assumptions you have about the type of image that you want to reconstruct. Okay, and this is encoded in this regularization term. And this is usually also the term where either if you look at an optimality condition, Euler-Lagrange equation, or a gradient flow of this energy, the PDE pops up, because it could, like in this case, contain a derivative of the image. Or, in the applied harmonic analysis viewpoint, this could be a term that penalizes in some way or the other the coefficients of the expansion that you have of the image U, and a very I would say the most popular condition and penalty that usually is used both for derivatives nowadays as well as for these coefficients in the expansion is a sparsity penalty, and the convex relaxation of a sparsity penalty on U is the L1 norm. Okay, so this is a long way to say L1 is a very standard example for a regularization term here. And here I'm taking the gradient of U into the L1 norm, which basically tells you that you're looking for U with a sparse gradient, meaning that you're looking for a good approximation of your original image by something piecewise constant, where the non-constant bits are the edges in your image. Okay, and in infinite dimensions, again, a good model for this is the total variation. So this is both, you can think of it as and there's a regularization parameter between them that balances out the regularization against the importance of fitting to the data. The regularization you can think of as a need to make this problem actually mathematically solvable, right? So in the case of X-ray tomography, the inversion of the radon transform is an ill-posed problem. So a way to make it well-posed is to regularize. Very often in imaging, in the kind of medical imaging and scientific imaging examples, is also an underdeterminedness problem, right? So you have less measurements than a number of unknowns in the image. Okay, so let me just skip this. We have seen, this is just to show you again, there's a drastic difference between the results that you get of your variational model depending on how you choose this regularization term. Okay, and we have seen this in the inpainting example before, right? The different results that you've seen in inpainting in the video with Samuli before, the differences really were mainly in the regularization term, in how you choose this regularization term. So this makes a huge difference. And there is a connection to differential equations. I alluded to this already, so let me jump over this. Let me go to the main thing, right? So it makes a huge difference of how you choose the regularizer. And lots of people have actually thought about and tried to come up with different ways to model regularizers. But this, I think, and we've seen this in the video, but this, I think, is a very good example of where learning can play a very important role. Because in all of the developments that we have seen, and I've been in this business now for almost 20 years, there are good things that come with these first principle kind of manually handcrafted regularizers, which are mainly in the theoretical results and the guarantees the robustness that you get from these models. But there are also lots of limitations of how fine-grained and fine-scaled your reconstructions can be, right? And so for people coming from PDs, I'm guessing, in a scientific computing seminar, probably lots of people come from PDs. You might appreciate that structures and images that are like texture, like grass, or repetitive, non-local structures are much harder to model than just local things that the typical PDs that we have can be modeled by. So here, learning makes sense, I would say. And one thing that we have been doing a couple of years ago by now is to parameterize the regularizer as a neural network. Okay, very simple idea. And in the spirit of what the regularizer should do in a minimization problem, namely distinguish between desirable and undesirable examples, so basically noisy and clean images, we trained this regularizer. Okay, and if you mathematically formalize I mean, what I've just said, that the regularizer should distinguish between the desirable, undesirable examples, you get a loss function that turns out to be the Wasserstein distance between the desirable and undesirable examples. I need to be a bit quick here so we can still have some questions. But let's say if you don't get all of this now, which I appreciate you will not, but we are just using, we are training this regularizer in some way, okay? And then we plug it back into our variational problem. We also impose some structural properties on the neural network. I mean, a prototypical one, of course, that you might want, because afterwards you solve a variational problem with this, is some kind of convexity, okay? That makes your life also easier once you actually optimize this at the end. So you put some thought into that, how you impose, here we use the notion of weak convexity, which is general enough to still be able to capture images as a class of objects that the network should approximate, okay? But it's also stringent enough to still have some guarantees on the optimization algorithm that you then use with this weakly convex neural network as a regularization term, okay? So you still get some convergence properties, which is basically summarized here in this theorem. It's really, just listen to me now. Sorry that I'm racing over these slides, but just listen. I think it's better to listen, not to look too much. So this is just telling you that it works. Okay, so this is what we did. We now compared this neural network regularizer in this context of computer tomography with a standard regularization term. Maybe I'll just go there directly. This is total variation regularization, so the one where we saw penalizing as a regularization term the L1 norm of the gradient of U. And here on the left, I'm always comparing with the ground truth. So I'm assuming this is all simulated here, that I have a super clean version of my object that I can compare to as a validation example. And this is what you get with the learned regularizer, which we called adversarial regularizer, because it's kind of adversarially trained between the desirable and the undesirable examples. Okay, and I mean, just going back and forth between those two, you can see that you get a lot more precision, you get a lot more details through the fact that you now really trained a regularizer very, very much adapted to the type of abdominal CT scans that it's being used for. Okay, so you can customize the regularization process much more towards what you want to solve. Okay, let me jump over this and let me go to the last slide, which really should put this in context. So this is really where I think the exciting developments in imaging are now happening, are at this interface between what we have learned from many decades of mathematically formalizing imaging tasks and whole frameworks of how to solve inverse problems, image processing, image analysis problems. But take advantage of the capacity of neural networks being able to model information and data, where the information that we are after here in the example I've shown is, how do images look like, right? What kind of images do I want to reconstruct? So I think it's a very exciting time. structure preservation here can come in two ways. It could be like in the example I've shown that you start out with a mathematical model and you plug in your deep learning component into an existing mathematical structure where you might again have some constraints on the neural network itself, like convexity. But the other way is to design neural networks, and that's again, I think PDE people can also actually have quite a lot of excitement here. A lot of developments have also happened where people have used PDEs as good parametrizations, as good role models of how to parameterize neural networks, right? And so in the inverse problems context, again, think of this as a CT reconstruction approach. This is another example where people have modeled the iterators in the network that should solve your computer tomography reconstruction problem as an iteration that takes inspiration from the variational model itself, right? But doesn't solve a variational model in the end. Yeah, and with this I finish, and I just leave you with these overall takeaway messages. Thank you very much for your attention.
Great, thank you very much, Carola. So we have some time. We should take some time for some questions. So I think Marie has a few, and then maybe she has some from the audience as well.
Yeah, so I have collected a few questions here. Thank you so very much for the talk, Carola. I'm so glad that we have a recording also of the slides so that one can take a look at some of these things in more detail. And especially, I really appreciate how you highlighted something that in a way is very obvious, but sometimes one forgets that, applied math involves using concepts from very many different areas of pure mathematics, right? And also bridging between these areas and leveraging aspects from different ways. So it was a very nice reminder for that. So I'm going to ask two questions here, I think. So one of them is the following. So you have worked with a range of applications and domains from a background in applied mathematics to zoology to art to medicine. How did these applications come about, and where do you think the math has been the most impactful?
So good question. So maybe let me start with us answering the last. For us, the most impactful work really has happened in the biomedical domain, and also in the cultural heritage domain, which are still the ones that are, I would say, the biggest focus areas in what we do. Biomedical domain is always tricky because the most impact I would say in the research that we have done has been on the level of medical research, really informing medical research studies. In terms of clinical translation and really turning some of these approaches into things that are being used, on a scanner, this usually takes a very long time. And so we have been collaborating with scanner manufacturers like GE or Siemens and so on, where up to now we've made it into their research software. But still, to take this to the next level, it just takes a huge amount of time, and yeah. So I would say this is the biggest impact, though. So it's really on the research level. And in the cultural heritage domain, the reason is just that this has been extremely overlooked by most of quantitative research, basically. And it is a source of really exciting problems. How do I find these? It's 50-50, I would say. It's 50. So a lot of times people approach us. I think it's also because of the name of the group. I think if someone looks for Cambridge Image something, then they find us because it's the Cambridge Image Analysis Group. So a lot of times I actually get approached. But other times it's also, like the typical thing that applied mathematicians do. They have a hammer and then they look for nails. So yeah, it's a combination of the two. Yeah.
And I just wanted to take the time to just ask this one question that we ask all speakers of the Langtangen seminars. So we asked you about what are your thoughts on what will define the state of the art in your field from your perspective in the next 10 to 15 years? And I guess what you ended with here is in that direction. But maybe if you want to say a bit more.
Yeah, okay, thank you, Maria. So I do think, while I think, from this it looks like very straightforward in a way to combine latest developments in artificial intelligence with the mathematical approaches we have been developing so far. Well, this seems, almost kind of straightforward how you would do this. I haven't really talked so much about the challenge. It is very challenging because there are really two communities meeting, two different types of philosophies, and the kind of guarantees, even mathematical things that you prove about these methods in machine learning and, let's say, PDEs is very, very different, right? And so I think in terms of thinking about this in the context of inverse problems and how to solve inverse problems, which is what I've been focusing on mostly mathematically in the last years, I think we need a new framework of how to mathematically formalize these approaches and also the kind of properties that we are asking of them. So there are typical things that inverse problems people ask about variational models, right? Well-posedness is something, but then there is also, null space property. There is something like source condition. There are certain tick-offs that people are usually wanting to prove, but they don't really fit so well to the AI components that we are now using or inserting in the models. So I think the state of the art in a couple of years will look, I think, very different, and we will see I hope we will see lots of new things coming up, in particular in the analysis of these approaches.
Agree. Thank you. Okay, back to you, Thomas.
Great. Yeah. So I also I have to catch a bus very soon, but I had a question that I was curious about because it went a little bit fast and I'm not so familiar with the topic. But when you learn this regularizer, you have to postulate a form of the functional, which I assume is taking in the image. But I guess you're viewing the image as a series of pixels. Is that correct?
Yeah. Yeah.
So then is the regularizer that you get specific to that device that was used to compute the images, or a device that has that number of pixels?
So it depends on what you're using, right? So what kind of parameterization you're using. I would say in the plain vanilla version, yes, you're trained it on one resolution, and then you get, the same kind of resolution you're using it on. But with things like neural operators, for instance, which I haven't talked about, but these are these are kind of scale independent in a way.
Yeah. Okay, that's where I was going with my question. So
Right,
on
you're
the,
going there, yeah.
you can
So
integrate.
it could be, yeah, you can use also you can set it up in that way as well. Yeah.
So you can like integrate a neural operator, and that would be essentially a kind of a regularization functional. And then
Yeah.
it's not necessarily dependent on the image, right? You can use it for other images, and that's kind of the attraction.
This is the attraction, right? And so I mean, maybe one more thing to say is, a lot of, I think what really differentiates the kind of work that people in mathematical imaging are doing, which is scientific imaging, medical imaging, and so on. And the same is also true in cultural heritage, as an example. We don't usually people there don't have the luxury of ImageNet, right? Of large image databases that you can train methods on. I think this is very different to computer vision. This is why I'm mentioning this. In computer vision and image analysis, let's say more on the engineering side of things, the main deep learning has basically solved problems there, right? So they are combining it with some mathematical models. Who cares, right? Because you can just solve it with with a deep learning hammer.
Mm.
This isn't true for these kind of problems.
Okay, very
Because
interesting.
you don't have enough measurements, and also the problems are more difficult, right? Because you have this forward operator in between.
Right, right. Great. So thank you so much once again for presenting today. We really appreciate it.
Thank you. Thanks for having me.
And just for anybody who's still there, the participants, remember this will be on YouTube after a brief bit of editing as soon as I get to it this week. And then we hope to see you all back next week for our next talk. So thank you again, Carola.
Thank you.
Bye.